So welcome, everybody. Since many of you don't know me, I'm going to give a quick introduction. My name's Michael Jantz. I'm an assistant professor in computer science at the University of Tennessee in Knoxville. My research focuses on building compilers and software systems to make computing systems faster and more efficient. At Tennessee, I lead the CoreSys research group, which stands for compilers, operating, and runtime systems. So those are mainly the software systems that we work on. Now, I've been working on performance and efficiency issues in memory since I first came to Intel back in 2012. I did an internship back then. So over the past few years, my students and I have really focused our efforts on building new tools and techniques to guide data management on heterogeneous memory architectures. In collaboration with and with support from Doshi and others at Intel, we've created a number of new software tools to help applications understand their own memory behavior and adapt to emerging memory technologies. We've also recently been working with researchers at Oak Ridge National Laboratory and other national labs to integrate this work with the Simplified Interface to Complex Memory, or SICM project, which is part of the DOE Exascale Computing Project. The SICM is an API and runtime system designed to allow existing applications to use complex and heterogeneous memory architectures more efficiently without really making invasive changes to the software, to the application software. So much of what I show you today is going to be labeled as SICM. That's because the work is now a major, or our work is now a major component of the SICM software. So I know Doshi's already shared with you some information about the design and results we've been able to achieve with these tools. If you're interested or want more information, I encourage you to read our recent publications of this work, which are also available on our group website. So for today, I'm just going to show you how to use our tools and show you some of the main capabilities that we've developed. And after the demonstration, I'm planning to post some of these examples, make them available to you so that you can have access and play with them yourself. Okay, so let's start with how to download our tools. I believe I'm sharing my screen. So I've got a document prepared called demo.txt here. So all of our tools are available in a public Git repository. So the first package that I recommend that you get is our SPAC repository. So if you're not familiar with SPAC, it's basically a package management tool designed to support multiple versions and configurations of software on a wide variety of platforms and environments. It's in wide use on many HPC and supercomputing platforms. So the SPAC repo we have for this project includes all the dependencies that you're going to need to build SICM, including the exact version of the compilers that we've tested and used with these tools, as well as the JE-malloc allocator. So SICM's built on top of JE-malloc as its base allocator. Next, you're going to want to get the actual SICM repository. So our latest tools are part of the HiDev branch in the SICM repo. So I recommend you check out the HiDev branch. Next, you'll want to build the tools. Okay, so I've got the commands for building the tools listed in this file. We have a very simple setup, so you just need to set a few environment variables and then go to the SICM directory and run SPAC install. Okay, so after setting these environment variables, so let me just show. I think I've got them set already. Yes. Okay, then you would go to the SICM directory, run some commands to set up your environment. Okay, and then you would run this SPAC install command. Okay, now this should be installed already. Yeah, so that command can take several hours to run, even on a bleeding edge platform, because it's got to build a whole compiler tool chain with lots of software. So if it's the first time you're building it, just plan on that taking several hours. Okay, so for this presentation, I've pre-compiled everything. Let's go back to demo.txt. So before going on, I'm going to give you a few details about the platform that I'm using for this demo. The details are listed in the file that's on your screen here. So this is a heterogeneous memory platform. It has 2 NUMA nodes and 2 types of memory on each node. Also note, we booted the machine in 1LM mode and configured it so that each memory device corresponds to its own memory node in the NUMA API. Okay, so when we set this configuration up, we've set it up so that we have 4 memory nodes in the NUMA API. Okay, so this is the output of NUMA-stat-m. It's telling you how much total memory you have on each node and how much you have free. Okay, so node 0 and node 2 are the memory on NUMA node 1, or I'm sorry, are the memory on NUMA node 0, and node 1 and node 3 are the memory on NUMA node 1. Okay, for processor 1. Okay, nodes 0 and 1 are the DDR memory, so we have 192 gigabytes of DDR memory on each node. And nodes 2 and 3 are the Optane memory, and we have about 500 gigabytes, 512, I think. Yeah, something like that, of Optane memory on each node. So some of the capabilities that I'm going to show you today, they rely on being able to set up this configuration. My student actually wrote a guide for booting and setting up a Cascade Lake platform with this configuration. So when I complete the demo, I'm going to post those instructions as well. I don't have those instructions in the file, but we do have instructions for setting that up if you'd like to see them. Okay. So next, to use the tools, we need to link them up against a benchmark or application that we want to use with the SICM toolset. So for this step,
hey, Michael, yeah, I just wanted to interject for a second and let people know. So the student that Professor Jantz just referred to, he is going to be at Intel until the end of June. So we can also work with him if there is any lack of clarity or if there is any help needed.
Yeah, his name is Ben Olson. Yeah, he's an excellent student, and he's very approachable, so don't hesitate to ask him any questions either. Okay, so that's the information about the platform. Let's show how to use the tools now. So I'm going to use a relatively simple application for this step. I'm going to use Lulesh. So Lulesh is a mini app that performs hydrodynamic stencil calculations, just some calculations that are widely used in HPC apps. It scales well with multiple threads and uses a lot of memory bandwidth. So we'll start by going into the Lulesh directory. Okay, so in this directory we have the tar file for the Lulesh benchmark. Lulesh is part of the Coral benchmark suite, so I downloaded this tar file directly from the Coral website. I also have a number of custom scripts that I'm going to use throughout the demo to show off the capabilities of our tool set. Most of these are directly from some private repos that we use to build and run applications of our research. But these scripts are simple enough. I'll go ahead and post these as well with the other materials of the demo on my website when I get a chance, or probably just after this demo today. Okay, so let's start by unpacking the benchmark. Okay, as I said, this is a relatively simple benchmark. We have a few. It's written in C and C++, so we just have a few CC and H files here. Now, to use the tools, we first need to make some modifications to the makefile. Okay. In the makefile, we need to replace the compiler and linker that it uses with some environment variables that will point to some scripts in the SICM software that we're going to use to do the build. Okay, so the changes we need to make are relatively simple. Okay. Oh, another thing I should point out, Lulesh can parallelize using OpenMP or MPI. Our tools do not yet really support MPI applications, so I'm using the OpenMP version for this, but we are working on building an OpenMPI version. Okay, so I'm going to replace G++ with a variable called compiler wrapper. Okay. Note also that this benchmark is getting compiled with -G, so that's important for one of the capabilities I'm going to show you. I'm going to replace the linker that is used in this benchmark with a variable called LD wrapper, okay? And that's the only changes we need to make to the make file. Okay. Now, before running the make, we have to set some environment variables, okay? So the build.sh script has, it sets up the environment appropriately to use our tools, okay? So the first several lines here are just setting up the environment, and it's going to point things into the SPAC and SICM directories. I want you to note the definitions of compiler wrapper and the LD wrapper variables. Those are what we used in that make file. So those are pointing to some scripts that are in the SICM directory. The other thing to notice is the definition of SH context. So our tools include a compiler pass to annotate each allocation instruction with a unique identifier. So by each allocation instruction, I just mean the individual malloc, alloc, realloc, or new instructions in your code. So SICM uses these identifiers to distinguish data allocated at different instructions in the source code. Now, for many applications, it's useful to consider not only the allocation instructions, but also some amount of call stack context leading to the instruction. So for instance, if an application defines a function like xmalloc and always calls malloc from the xmalloc function, our tools would only find one allocation site in that application. So for these cases, we include an option to clone functions in the call graph on the path leading to the allocation instruction. So in this way, the resulting executable will contain multiple distinct allocation sites for allocations that reach the allocation instruction from different call paths. So SH context controls the maximum amount of call path context to clone for each allocation site. So setting it to 3 tells the compiler, let's clone up to 3 layers of call stack context to distinguish allocation instructions reached from different call paths. So if we set SH context to 0 here, the compiler will not do any call path cloning during the build. For most of our experiments that we've been running, or a lot of our experiments we've been running, we typically use SH context equals 3 because we found that 3 layers of context tends to work well for most applications.
Sorry, a question.
Yes.
So when you say 3 levels, do you mean 3 levels from the top or from the bottom?
From the bottom. So it's looking at the leaf that's calling malloc, or maybe it doesn't have to be a leaf, but it's looking at the node that's calling malloc in the call graph, and it's looking at the parents of that node, and it's moving backwards up 3 and then cloning those parents if it is reached by multiple distinct paths. Does that make sense?
Yeah. Okay. Thanks.
Okay. Okay.
Question.
So this is
sorry.
Oh yeah.
Yeah. So how the overhead depends from the number of contexts?
So what this really does is I'm going to show you how this works, but what we're doing is we're estimating memory behavior and estimating the memory behavior for data allocated at different sites in the program. Okay, so if you have more allocation sites in your application, that will have more data points and more ways to control where data goes in the application, okay? If we only have one allocation site, our tools would only profile that one allocation site and would aggregate all the memory behavior for that one site into one bucket. Does that kind of make sense? I'll show you more of the tools in just a sec. Maybe that would help clear it up as to why we have this mechanism.
Okay, yeah, I understand how this variable impacts number of context and aggregation, but I'm interested about runtime overhead when we run the tool.
Oh, are you interested in, like, does this add overhead to the application if we do this?
Yeah.
Is that what you're?
Yes.
Typically, in the cases we've studied, like we've studied this with multiple benchmarks. You can look at our papers, but we have found very little overhead, basically no overhead for doing this kind of transformation. Okay, and we could I could actually show it out on this Lulesh example, but that information is also in our papers that's on our website.
Okay, got it.
Yeah, the one place where there might be some overhead, but it might be trivial, would be in the growth of the code size, because you're repeating some amounts of code, but that's about it, right?
And that's also why we typically limit this to 3. If you we tested it with up to, I think, 8 layers of context, but if you get much past that, your executables start to get quite a bit bigger. And so, yeah, the growth of the code size could have an impact also on your performance. Okay. Okay. Anything else? All right. So I'm going to run this script. So I run build.sh. Okay. So that build, it creates an executable that links against our SICM tools, as well as a few informational files that we've used for our experiments. I'm going to ignore most of the informational files, but I do want to point out this context.txt file. Okay. So this file includes all the allocation sites that were identified during the build, as well as the unique identifier that was assigned to each site. Okay. So the numbers on the left show the ID for this site. Oh, sorry. Numbers on the left show the ID that we used for the site, and because we compiled with -G, we also have the file name and line number of the actual allocation site in the source code. So, like, if we look at this first site, okay, and we look at lulesh init.cc, oops. Oh. And we look at line 388, it's already on line 388. We see there's a new instruction here. So this first allocation site corresponds to this new instruction in your source code. Okay. The file also includes information on the context leading up to the site, but the context is expressed as symbols in the LLVMIR.
Sorry, a question here.
Yeah.
So you have a compiler wrapper. Which compiler are you really using to compile the code here, to instrument malloc and mallocs?
It's Clang, so it's LLVM. Basically.
Okay. It's a modified LLVM?
Yes, and the pass works on the LLVMIR.
Okay, I see. So you instrument malloc. Do you also instrument free?
There's no need for us to instrument for this pass. There's no need for us to instrument free. We're just identifying where data can be created with this pass. Now, the SICM runtime does intercept the free calls, okay, because it's controlling the memory management of the application.
So what if memory reused? You allocate free, then reallocate again as reused.
A realloc is counted as a new allocation site.
No, I'm talking about the reuse, the memory you freed. The same virtual address. You have the same virtual address, but it's reused.
It depends on where. So the way the are you asking like how would our profiling tools assign that memory?
Yeah, I'm asking really just you at phase 1 of the program, assume you have an OpenMP of regions. In region 1, you allocate a bunch of objects. Then at the end of region, you free the objects. So next phase, you allocate the objects again, but they reuse the memory just freed in the first phase. But they got the same virtual address.
So yeah, you can reuse the virtual addresses, but what would happen then is our tools would say, oh, okay, these new virtual addresses, they've allocated some new objects into these virtual addresses. These objects are associated with allocation site X, whereas before the virtual addresses were associated with allocation site Y. And so the profiling tools will associate the profiling at that point with allocation site X. But at the point that allocation site Y has its data in those addresses, they would associate it with allocation site Y.
Well, I heard you only use the 3 levels of context, but I'm talking about really. So I guess my question is really, you cannot distinguish the allocation site from the 3 levels of context, but the memory is reused. Yeah, if you can have if you have all the 3 levels, can distinguish all the uniquely identified allocation site, that's fine.
Seshan, let me jump in and steer it in a direction. So what's happening here, right, is that these sites are getting annotated, and that annotation is going to be associated with the memory that is allocated at that point. The free is going to the free does not matter, because at the next time that same buffer, right, memory buffer gets reallocated, it will be associated with the 3 layers of context, right, that would be for its new incarnation in life. So at that point, right, all of the heat map that is generated against that buffer would be associated with the new context instead of being associated with the old context.
Does that make sense? That's what I was trying to
yeah, okay.
Earlier.
Yeah, I got it. Okay, thanks.
Okay. Thank you, Doshi. Okay. So before moving on to running the code, I wanted to show you. So Lulesh is a relatively simple code. Its call graph is relatively flat. And when I ran this example with 3 layers of context and with no layers of context, I found, I just moved to the bottom of the context file here. I found there's about 90 sites, regardless of if you use context or not for Lulesh. So to make this a little more interesting, I compiled another benchmark earlier, and I compiled it with no context. So this is a magic, or it's image magic from the CPU 2017 suite, spec CPU 2017. So with no context, you can see it has 6 allocation sites. Okay, there's a file called magicmemory.c, and this is it's a function called acquire aligned memory, and they have functions like acquire virtual memory. So this is the situation where you've got everywhere in this larger application is calling into these into a small set of functions. Now, if we add 3 layers of context, the number of allocation sites balloons quite a bit. Okay, so now this is the context.txt file with 3 layers of context. Okay, and we can see, memory.c line 274 corresponds to many different allocation sites here. Okay, and actually these functions that say __ compass, those are cloned functions that our tool created in the call graph. Okay. All right. So now we've got a built version of Lulesh that's linked against SICM. So now we can use SICM to profile and guide memory usage on our platform. So most of the options and configurations in SICM are controlled by setting different environment variables, which you're going to see as I go through the rest of the demo. So first I'm going to use our tools to simply run Lulesh using the SICM allocator. So for this run, I'm going to use the run unguided script. Okay. There's a few things to note in the script. For all the experiments in this demonstration, I'm going to use NUMA control to bind the application threads to only one processor and bind the allocation's stack memory to the faster memory device. So our tools don't yet support placement of globals and stack memory, so we use NUMA control for that data. In the case of Lulesh, the globals and stack actually don't contribute a significant amount of capacity. So, and for the case of a lot of applications, actually. Also note we're setting OMP num threads so that Lulesh creates 48 threads. The processor we're using has 48 hardware threads, so we're just setting this value to utilize the parallelism in Lulesh. SH default node controls where each data allocation will be initially bound if there's no additional guidance from our tools. So in this case, we're not passing additional guidance, so we're binding all heap allocations to the faster memory on NUMA node 1, or the memory node 1, okay? So if you look back at NUMA-stat-m, it will go on node 1 in this output, okay? Also want to note here.
Sorry, so you meant node 0, right? Because you said node 1, but you.
Yeah. I'm sorry. I meant it's going. So we've specified SH upper node here. These are the memory nodes. Okay, it's actually going on to processor 1, DDR4 memory. Okay, so that's the DDR4 memory in processor 1. For all these experiments, we're going to bind everything to processor 1. This should be this SH upper node. I should probably have a different variable for that, but yeah, the SH upper node here refers to the processor node. Here it refers to the memory node 1. Okay. Okay. So let's go ahead and run this example. So we'll just run unguided. Okay, so this will take, I think, like 45 seconds or so. You can see it's consuming some of the capacity on node 1 in this. This is the output of NUMA-stat-m. Okay, and if we look at top, Lulesh is consuming, close to 4,800% of the CPU. Okay, so it's using all the threads on this processor and using some of the memory in the DDR4 device. Are there any questions at this point? This experiment will just take a little bit to finish up.
When you're saying that it takes one processor, you mean like one socket, right?
Yeah, one socket. Yeah, one socket. And the socket has it has a processor with 24 cores, and the cores are hyper-threaded. Yeah.
Okay.
Okay. So that script shows how we can run Lulesh with SICM, but it only uses the default allocator. If we want to use some of the other capabilities in SICM, we have to specify a few additional environment variables. So next, I want to show you how to use our tools to profile the memory behavior of the data associated with each allocation type. So for this, we're going to use this run profile.sh script. Okay. So in this file, we have some of the same variables that we used before, but I've added and changed a few of the options. So first note that we're setting OMP num threads now to 47. So for a lot of our profiling configurations, we reserve one of the hardware threads to collect the profile information and allow the other threads to execute the benchmark. So that's the part of the overhead of the profiling is we just take away a core and let the profiler operate on that one core. Our profiling configuration also used this arena layout option called shared site arenas. So this option assigns the data from each allocation site into a page-aligned region of memory known as an arena. Okay, so basically this approach ensures that the data associated with each site does not use the same set of virtual pages as any other site during the profile run. Okay, so this can fragment the memory, but again, this is only during profile. It also facilitates the collection of profiling information for the data associated with each site. Okay, so it just makes the profile run faster. We have SH profile all and SH profile all events. These turn on profiling of memory accesses using the PEBS facility on our processor. So specifically, SICM uses the perf library to collect the PEBS samples. And then the options in this script tell SICM to sample memory accesses that miss the last level processor cache. And the profiling tool in SICM then keeps a count of sampled accesses for the data associated with each site. A few other things. SICM has a few different methods for estimating the capacity of the data associated with each allocation site. This SH extent size option measures the number of bytes that are allocated and in use for each site over regular intervals, and then reports the maximum capacity interval for each site. And then the remaining options here just control the rate of profiling and specify the name of the output file for the profile information. Okay, so let's go ahead and run this example. Okay, so just double checking everything. Looks like it's running, still using most of the processor, and it's using the same memory device. You'll notice there's a little bit happening on node 0. That's probably some system services or something like that. We can't get the machine completely idle for all of our experiments, but most of the work's being done on node 1 here.
So, Michael, you'd expect that this would take a little longer than the first run, right? So the first run was 45 seconds.
Yeah, the first run was 48 seconds, but the overhead of the profiling is actually, pretty quick. Like here, it was almost imperceptible. This is not a throughput benchmark. It's not a benchmark that just runs for a specific amount of time. It's actually, it should take a longer amount of time depending on the performance, but the performance overhead here was pretty negligible, even though we took away a core to do the profiling. Okay. So, but yeah, we have found cases where the profile can generate quite a bit of overhead, but for the most part, especially on these newer Cascade Lake platforms, the profile overhead is pretty small. Okay, so let's look. So this creates a file called profile.txt. Okay, or we specified that file name in the run profile.sh script. So let's look at this. Okay, the output of this file is not great to read, but what we're seeing here is that run, it created an arena for each allocation site. And you can see we print out information about the profile data in that arena under it, okay? And what this is telling you is that arena 0 had data from one allocation site allocated to it, and that allocation site was site 54. Okay, so the way this run was set up, so all of the data from Site 54 was allocated to Arena 0. We do our profiling in intervals, okay? And this is the number of intervals that the profiler executed.
Sorry, a question here.
Yeah, go ahead.
So when we talk about the arena, you're not talking about the arena of the JE-malloc. You're talking about each allocate has arena. I just want to make sure
it's built on top of JE-malloc, and I'm not sure exactly what you mean, but yeah, the arena allocator in JE-malloc, it's using that same subsystem.
Yeah, well, I'm asking, your arena is the same as the JE-malloc arena.
Yes, yeah, it is.
Okay.
Okay.
Okay, thanks.
So what we see is this is telling us that the data at Site 54, we sampled 29 memory accesses that missed the last level cache throughout the total run, throughout the entire run for the data at Site 54. Okay. And the data at Site 54, we estimate its capacity was at a peak around 2 megabytes. Okay. You could compare this to some other sites. So if we look at Site 38 down here, okay, it had quite a few more accesses, so 72,000 sampled accesses, and it consumes a bit more capacity. So the Site 38, generated more data and was accessed quite a bit more by the application. Okay. Next.
So what is the, sorry, so you have the, for take the example here, the event total is 72,664, that many samples. What is the sample rate?
The sample rate, I believe it's defined in
profile.sh.
Yeah, and run profile.sh. That's what these options are doing here. Profile rate in seconds, I think that is the interval rate, and that's used internally in our JE-malloc software. And then sample freak, I believe, is the PEBS rate, but I'd have to look that up. I'm not the developer of all of these tools. My students put this together, but I believe.
Oh, that's fine. Yeah.
Yeah. Yeah.
Okay. 128.
Is the event frequency for PEBS. Okay. So next, we also have tools that take this profile information and use it to automatically provide recommendations for which data should go on the high performance memory. So our main tool is named SICM Hotset, and it's also part of the SICM repository. Okay, so let's look at this. So we have a script called hotset.sh. Okay, and this shows how to invoke this tool. So SICM Hotset, it takes some profile information on standard in and outputs a guidance file that can be used by a guided run of SICM. Okay, so the main arguments here are the capacity. This is the assumed capacity of the high performance memory in bytes. And so in this example, we're using NumaStat up here to get the total number of free bytes for the DDR4 memory that we're using in this experiment. Okay, so that's the assumed capacity of the upper tier of the system. Weight is the profile data that describes the capacity or weight of each allocation site. So we used extent size profiling to profile the capacity. So that's just telling it in the profile file, you're going to find the capacity labeled as extent size. And then node is the memory node in the Numa API associated with the high performance memory. Okay, so SICM will use this in the guidance file to bind data to that node. Okay, so basically this script, it implements a bin packing algorithm to assign sites to the high performance memory tier until their expected capacity exceeds some assumed maximum capacity. So our research has evaluated a few different heuristics for performing this task. Typically, these heuristics are based off sorting the sites or using like a traditional knapsack approach for bin packing. For today's demo, I'm just using a very simple sorting-based technique. So this approach sorts the sites by the number of sampled accesses per byte of capacity, and then adds sites to the high-performance tier until the combined capacity of all the added sites exceeds the assumed capacity of the upper tier. So in this case, since the assumed capacity is the entire free memory on NUMA node 1, and the peak resident set size of Lulesh is only about 10 gigabytes, it's going to add all of the profiled sites to the high performance tier. Okay, so if we run this, okay, it runs, and then we can look at the results in guidance.txt. Okay, so this is the guidance file. Okay, so this file, what it's doing is it's listing all the allocation sites for which there is guidance by their integer ID. And then next to each site, it lists the NUMA memory node that SICM should use to allocate data created by the site. And since the SICM hotset script assumed the high performance tier has more capacity than the entire benchmark it will use, it assigns all the sites in Lulesh to the DDR4 memory. So if we look, we have all the sites here assigned to the DDR4 memory. Now to use this file, we conduct a guided run, and I have a script for setting up a guided run in run-guided.sh.
Actually,
okay,
can I stop you for a second? So in the guidance file, I'm assuming you have a variable that tells it how much capacity to assume instead of assuming everything, right?
Yeah,
so that you can generate a guidance for some other machine that might have, let's say, just only 8 gigabytes in the upper tier, for example, because Lulesh is so degenerate, right? It is so small that it fits entirely.
Exactly. I was gonna show off that capability here in a sec, but this, yeah, you can look at hotset.sh. That's one of the arguments to the script that creates the guidance file is the maximum capacity, the assumed maximum capacity of your upper tier.
Okay. Sorry. Yeah. The only thing is that just a very quick time check. You have about 14 minutes left, and you probably want to leave about 5 minutes at the bottom.
Yeah. Let me. So let me go over run guided. Okay. This shows how it sets up a guided run. Let me talk about some of these arguments or some of these variables. First, it uses a different arena layout. So again, we're using 48 threads again, but it uses a different arena layout. So this option, this exclusive device arenas, it tells SICM to create distinct arenas for each type of memory for each thread. So on this machine, each thread will create exactly 2 arenas, one for objects allocated to the DDR4 and another for objects allocated to the Optane DC memory. Okay. The low-level SICM interface then uses mbind to bind each arena to the appropriate device. Okay. Note also here that I've changed SH default node and now set it to the lower node. So that is the Optane DC memory. Okay. So if there is no tier guidance from the high-level interface when the application allocates a new data object, the object will be assigned to the Optane memory by default. And then the only other thing in here that's of interest is this guidance file option. So we specify where the guidance file is through this environment variable. Okay, so since we're low on time, I won't run this, but if I were to run this, basically what would happen is it would run, and it would run in about the same amount of time as the other experiments I've run. It would take about 48 seconds because all of the memory is still going to the DDR4. If you would like, now, however, we can exert fine-grained control over where data associated with each site goes by just editing the guidance file. So you could do this by hand if you want. So I'm going to take the last few sites here. I'm going to assign them to NUMA node 3, which is the Optane device that's on the same processor that we've been running the experiments on. Okay.
Sorry, a question here. A quick question.
Yeah.
So when you rank the allocation site, the hotness of the memory object, do you rank by the L3 miss event numbers?
Yeah, so it's the L3 misses, but normalized by the capacity estimate as well.
Okay. So the more miss, the hotter or colder?
The more misses indicates there's more accesses to that memory. So yeah, the hotter the device, the hotter the memory.
Okay.
Okay.
Okay. Thanks.
Okay. So I'm going to run.
So I still have a question about overheads. So on when you run guidance, so it means that for every allocation you should understand the call stack, right? And it requires significant.
So yes, that's a very good question. So that's one of the benefits of having the compiler pass like we do, is we don't have to dynamically determine the call stack. Okay, we annotate the executable with the integer IDs. Okay, and so since the executable now has cloned the functions in a way that the call paths are distinct up to some number of nodes leading to that site. Okay, and so we can. Yeah.
Sorry. You mean that it's some kind of sequence ID, right? So for each particular, but how you deal with multi-threading? It's per thread, or because I understand how it can work in a single-threaded environment, and in case you have a predefined order of allocations, but if your application have some set of randomization, then the allocation order can be different from run to run, right?
This doesn't really have to do with the order. It has to do with where the data is allocated from in the executable. So that is not going to change regardless of if it's allocated from thread 1 or thread 250.
Yeah, but my question
from the same instruction, it'll get the same ID. So sorry, yeah, go ahead.
Yeah, but my question is how to distinguish allocations on the second run, on the guided run.
Oh, I see what you're saying. So yeah, so those annotations are static from run to run. So they're actually installed into the executable. So the site 10 in run 1 is going to be site 10 in run 50. It doesn't change from run to run. Does that answer your question?
I think so, yeah. So it means that there is a limitation for this too, that the allocations should go every time in the same order, right?
No, the allocations don't need to appear in the same order. What this tool relies on is that the source code does not change from run to run. It's right. Really using static annotations from the source code.
Sorry, but what I don't get here is that you say that you annotate allocation sites and you have some deduplication by the compiler. So I imagine I'm having like a helper function which allocates me some object to be used later by my code. In this case, I can easily see how a compiler can make a tag, can place a tag on this allocation place of this helper method, say a constructor or something, but I cannot see how I can distinguish using this object from one or another place in my code.
That is the reason why so the use of that particular allocated memory buffer is what the web's profiling is going to put out to point out, right? How hot is that buffer? But that,
no, I mean, let's say I have a very common object, like a common buffer which can be stored in whatever, and I have a helper function which allocates me this buffer. So basically, I can be calling and making this buffer from all over the place of my code, and in some places of this code, this buffer would be hot, and in some other it would be not hot. Just because it's being made from a helper function, it doesn't mean anything. I mean,
yeah. So
if we dump my example down to a very strict level, let's say that you somehow instrumented the malloc function. So not the results of the malloc, not the call side of the malloc, but malloc itself. Or like if I have a wrapper around malloc function, which I exclusively use in my code. In this case, all objects would have the same call side, but they would be used differently, and they would be they would have different temperature in terms of hot and cold. So how do we deal with this?
So that's what the context cloning is for. So the way the malloc gets reached is what the tool cares about. Where the path to the malloc is what the tool cares about.
So it's possible to extract the call path in the compile time. This is what you're saying, right?
Yes. So we get that statically by basically cloning paths to the call to the allocation instruction. And so we find all the different paths in the call graph that can reach the same allocation instruction. We clone those paths so that they're unique, and then we annotate each unique allocation instruction with its own identifier.
What if my executable uses some, I don't know, some runtime dispatching or something? This is not going to happen, or?
Yeah, so that case we do not cover. So like virtual functions, that sort of thing. Yeah, that would not be. So dynamic parts of the call graph like that we could not discover statically. That's correct.
The way to do that, Brad, would be to use a higher overhead method, which we are not showing here, but you could instrument that with a backtrace, and with the backtrace call, right, you can now disambiguate the different paths.
Yeah, but backtrace is insanely complex in terms of how much time you need to spend.
Correct. Yeah, so that's a trade-off, right? The trade-off is between making sure that we can use this for a majority of good purposes, right? And there will always be these corner cases.
I see.
And then the other thing is that if as code developer you already know what you're trying to do, right? Then you can go ahead and edit those intermediate text files, right? And not depend upon this kind of disambiguation being done by the compiler.
This is not something I would be following probably, because I saw a lot of times where a developer thinks he or she knows about the code, but it's not true. It's usually not true.
Yeah, that's true. I mean, so we are really trying to do something that is reasonably theoretical, but is immensely practical. That's what.
Yeah. I see. Thanks.
Yeah. So the other thing I'll just point out is so the guidance file tells you all these sites. I won't run this because it will take a little more time, and I know we're at the end of the meeting. If I were to run that, it would show that, this takes a little bit longer now. So it takes about a minute and a half or something like that after I move those sites to the Optane memory. The only other thing I wanted to show was, Dosha, you had asked, what if you restrict the amount of memory that's available that the hotset script assumes. And so here, this code here basically finds the peak resident set size of the Lulesh application, and I'm multiplying it by 0.5. Okay, so I'm taking half the resident set size of Lulesh, and I'm passing it to the hotset script. Okay, so I run that. And now if I look at the guidance file, it's still got a bunch of allocation sites in here, but it's got way fewer than it did. Okay, so I think it has about 50 in here, whereas before it had 90 or something. And that's because it's finding the hottest sites to pack into the upper tier of memory. Okay.
Good.
All right.
So when you run, sorry.
Go ahead.
Yeah.
So assume when you use the PEPs events to get the data linear address, use the data linear address to map back to the object, right? Allocation object.
Exactly. Yep.
So then you use the number of L3 cache misses to determine whether that object is hot or cold. So have you found the case that inside just one object, one cache line is really hot, the other cache lines are really not hot?
So I've seen.
So what do you do? Do you classify that as hot or cold?
So I've seen work that explores issues like that. We have not tried to tackle that with this particular work as yet.
Okay.
Yeah, but there is
plus your own work, right? For energy guidance, right? You had sliced objects, right? So you push the hot.
Yeah. There are some techniques, especially in like high-level language runtimes, like in a Java VM or something, where they'll rearrange fields in a struct or something based on the hotness of certain cache lines and things like that within a particular object. But this work, the unit that it's doing the profiling over is the allocation site itself.
Okay.
And we found that can be pretty useful on these types of architectures and for this data tiering problem.
Yeah, it's really application dependent here. So assume what you're doing here is if even one cache line inside that object is hot, you classify that object is hot. Is that correct?
Exactly. Yep.
Okay.
But that depends upon the size of the object, right? So if it's one cache line that is hot in an object that is 1 megabyte large, right, then that object will be considered to be cold because it's access to the number of accesses divided by the density. And then with regard to your one hot cache line problem, that's actually something that the processor caches are already helping us with, right? Because the processor caches are going to actually absorb very hot cache lines in very cold objects. So in effect, right, we are really trying to do well for things that are not captured by the processor caches, but which therefore need to be still be given the upper tier preference if their overall access density over the entire object, right, is above some threshold.
I have a quick question. Do you have any plans to use this, or is there any way to use this as a library? So instead of the static instrumentation, do something dynamic, especially useful with dynamic allocators or custom allocators?
So we haven't. Are you talking about like building the profiling into a tool that wouldn't require any sort of recompilation of of the executable?
Because if you have a custom allocator, you want like something like this, but dynamic feedback mode. So
we would like to do something like that, but the first thing when we started doing this work, one of the big problems we came across was the overhead of doing like call stack tracing and that sort of thing. So we've gone to this static approach that relies on static annotations in the compiler. It would be interesting to see which sorts of applications we could get away with doing this in a completely dynamic way. I think that would be a good direction. Yeah.
Yeah, and Eric, this is actually one of my strong interests is that in managed runtimes, it should be possible to pack self-profiling into the managed runtime in order to complete the loop we are talking about.
Okay.
Yeah. Managed runtimes would make a lot of this easier. Yeah.
Okay.
Any other questions?
We ran out of time, so unfortunately, we need to switch to different meetings. Thank you very much, Michael.
All right.
Very much.
Thank you.
I'll see what I can do with the recording.
Yeah, and Eric, there were no sensitive questions asked, so I think we should be perfectly fine to let this recording be available also from.
Yeah, agree.
Okay. Thanks.
All right.
Thank you.
All right. Thank you.
Thank you. Bye.